For most of human history, we have been completely at the mercy of the weather. Today, as we stare down severe land droughts and record-breaking ocean temperatures, that passive mindset is colliding with a stark reality. In 2012, satellite imagery revealed something curious over the Pacific. Notice these bright, winding cloud tracks behind commercial vessels. The soot and exhaust acted as an atmospheric catalyst, accidentally making the clouds brighter, actively cooling the ocean below. This accidental discovery proved that human pollution could lower ocean temperatures. It naturally leads to a massive question. Could we intentionally engineer the sky to save us from our own climate and water crises? We are quietly transitioning from victims of the weather to active climate engineers. To understand how we wield this power, you have to look past the massive storm systems and zoom all the way in to the microscopic engines of the atmosphere. Right now, targeted weather modification is already being deployed over highly vulnerable watersheds. It relies on a mechanism called cloud condensation nuclei, or CCN. In the atmosphere, water vapor can't just condense or freeze on its own. It needs a physical base, like a microscopic piece of dust or salt, to latch onto before it can become a heavy droplet or snowflake. Organizations like the Desert Research Institute hack this physics. They shoot a compound called silver iodide directly into winter clouds to act as artificial condensation nuclei. This chart shows the direct result of that process. By measuring the runoff, we see that these ground-based generators can push regional mountain snowpack 10 to 15% higher than natural baseline levels. Shooting chemical compounds into the sky inevitably raises a serious concern. Are we poisoning local ecosystems to get more water? The chemical data tells a very clear story. Silver iodide is virtually water-insoluble. Furthermore, it is dispersed in parts per trillion. Because of this, it passes through the environment without biologically accumulating in lakes or local wildlife. By manipulating microscopic particles, we can safely generate local precipitation. But generating water only solves half of the climate equation. To cool the Earth's temperature, we have to scale this logic up and take it out to the open ocean. This is the premise of marine cloud brightening. Instead of silver iodide, engineers propose scrying microscopic sea salt into marine stratocumulus clouds. Getting that salt into the sky requires massive infrastructure. The current blueprint calls for fleets of autonomous ships, equipped with towering rotors, pumping seawater mist directly into the lower atmosphere. This triggers the Twomey effect. When you inject extra salt nuclei into a cloud, the available water vapor is forced to divide itself into millions of tiny droplets, rather than clumping into a few large ones. This incredibly dense grouping of small droplets acts like a massive mirror in the sky, aggressively reflecting incoming solar radiation back out into space. Localized testing of this sea salt deployment is currently underway to cast shade over highly vulnerable ecosystems like the Great Barrier Reef in Australia. Armed with seawater, wind, and basic physics, humanity now possesses the theoretical blueprint to build a planetary sunshade. These localized experiments show that we can induce rain or cast shade with technology that is relatively inexpensive, fast-acting, and reversible. But deploying these tools at a global scale exposes a fatal flaw. The Earth's atmosphere is a deeply interconnected web, meaning local actions inevitably trigger distant reactions. Climatologists refer to this phenomenon as teleconnections. If you artificially brighten clouds in one hemisphere, you alter currents thousands of miles away.
For example, cooling the western U.S. could severely disrupt Atlantic currents. That shift would cause punishing heat waves across Europe and pull rainfall away from Central Africa. We have demonstrated the mechanics needed to manipulate clouds at the microscopic level, but until we can accurately map and predict these global chain reactions, flipping the switch on planetary geoengineering remains our greatest gamble.